Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hello and welcome to our second Australian Water School webinar on fish passage, dedicated to Australian species. I'm your host, Craig Price, and I'll be joined today by engineers and fisheries biologists who will step you through a range of techniques for modeling, designing, and assessing fishways. Let me introduce our speakers today. If you can all start turning on your cameras and mics as they're coming on. If you haven't had a chance yet to check out our first Fish Passage webinar, we will include links in the chat line and in the video descriptions for you to check out later. Thanks also to the attendees, to everyone who filled out the poll results. We will have a look at those momentarily in the background once our presenters have had a chance to introduce themselves. So we've got today with us Steve, Kyle, Tim, if you can all just turn on your cameras and mics. What I'd like to hear from you about, first of all, where are you coming to us from? I'd also like to know whether you started your career and your education dealing with fish, or did you move into this field from another area of focus? So kind of in the order that we've got here, let's start with Steve. How did you get into this business, and how long you've been at it?
Yeah, good morning. Yes, Steve Slark from Jacobs here in Adelaide. I got into the business about 20 years ago by default. I moved to Australia, and I was given a project working on the River Murray, and just happened across doing projects with regulators and fishways.
Sounds good. All right, over to you, Kyle.
I was going to say 20 years later, Steve, still doing it. I'm Kyle, based out in sunny Brisbane. I actually started doing civil and construction engineering. And then I think as most disciplines go, you kind of trip and fall into a certain discipline. For me, it was water engineering, then, onto CFD, more advanced hydraulics, and now it's fish passage design.
All right. Well, Kyle's going to be sharing some pretty cool animations with us today. Over to you, Tim. Let's hear from about your background. First of all, where are you coming to us from today? Because this is a little bit exciting.
I'm actually coming from a very rainy Cambodia at the moment. So we're over here doing some fish passage projects with our Cambodian colleagues. I actually came to fish passage via geology. I actually did geology at uni. And discovered that I like fossicking, not actually all the ins and outs of coal petrology, and moved into the fishy field, and have been here now for 30 odd years doing the fish passage stuff. So it's great.
Awesome. Great. Well, let's have a look at the poll results here. And thanks again to everybody for filling those out. A wide variety of backgrounds. It looks like a few have modeled before, but most of the attendees today, we've got several hundred registrants today, most have not modeled. So that gives us a little bit of a good feel for, what we're going to focus our presentations on today, and how far back we need to go on in terms of the basics of modeling. There is a pretty even spread on the types of fishways everyone's worked on. Myself, I was involved for about 15 years of my career with the U.S. Army Corps of Engineers, doing some major fishways across dams, and then some backwater pools and things like that on side channel restoration projects. So it's interesting to see this full mix. Any comments? Kyle, I'll turn it over to you. Any comments on the poll results, and then we'll go ahead and get cracking with the presentations.
No, I think it's just good to see how broad the different types are, how evenly split it is. And, if there's 19 people that have worked on locks and gates and mechanical structures, that's fairly impressive.
Yeah,
they're normally quite unique.
Yeah. Excellent. Tim, Steve, any other comments on that?
It's really interesting just to see how many people are working with road crossings at the moment. It's a real big focus in particularly Queensland. There's lots of fish-friendly road structures going in throughout the state, and it's good to see so many people working on it.
Yeah. Great. So last time around, we did one about a year ago. We did a webinar covering fish passage, and it's all, even though some people were coming to you from Australia, it was all American accents, and a lot of people who were involved in Pacific salmon and high jumping species and fish cannons and all sorts of things that we talked about there, the fish ladders. Some of those designs have been implemented in Australia unsuccessfully and without consideration for the jumping limitations and things like that were local. So we had the request at the time from many of the participants, hey, let's get deeper into the Australian species, being the Australian Water School. So in response to your feedback, we do listen. So, let us know what you want to hear of more next year. This is in direct response to the feedback from our previous part 1. Here we are with part 2. So Kyle, if you want to, Kyle's going to be your host today. I'm your host facilitating this. Kyle's the technical manager of all of what you're going to see here next, and he's going to pass things back and forth between Steve and Tim. Over to you, Kyle. We can see your screen just fine.
Awesome.
The rest of us will mute out. Keep those Q&A questions coming, all attendees. Keep those coming in the background because we'll hit those in the end during our panel discussion. So over to you, Kyle.
Cool. Thanks, Cray. And I just want to say a quick thanks to Tim and Steve for coming today. I think between the two of them, they've almost hit 50 years experience. So in terms of Aussie experience, it's absolutely great having them here today. I'll start off with an introduction on Aussie fish passages. And here in Australia, passages, these modern larger structures tend to be one of these 3, the large step pool weirs, mechanical weirs, and I guess consideration for downstream passage. So I'll focus on them mainly and then start talking about briefly the fish passage design process. And the big thing here is how you actually need a team of, you need a good team of people to deliver a working solution. So before we get started, I have 3 fishways here. And question for our audience, which one of these was built in Australia? So the first one here on the left, this is a vertical slot fish passage constructed next to a waterfall. And what's quite nice to see is this calm condition at the entrance. So fish, as they approach, ideally they'll find that calm condition and work their way upstream. The steps are quite steep between each. So you'll probably end up with higher design velocities. Second one here, this is a spiraled stepped weir spillway. Calm conditions again at the entrance, so that's quite nice, but you can see there's quite a steep grade going through that spiral. And the third one, this is a cone fishway connected to a weir. Looking at the pool of that cone fishway, you can see it's quite calm conditions, except for that small plunge that occurs at the downstream. So onto the audience briefly, which one would be the Australian fishway? That one on the left, that's one in Iceland. And those steep steps mean you have very high design velocities, maybe 8 meters or 10 meters per second. So the fish that can get through there, that's that Atlantic salmon that can throw themselves out of the water. You're not going to be seeing any of that in Australia. The second one, it's an interesting folk tale online, but apparently that second one was built in the 1930s for salmon passage, but neither the water body or the dam itself is stocked with salmon or have any salmon. So the online story goes that that's, a nice paperweight, basically. It's a good reminder to think about your biology before you dive into any of this. The last one, that's the Fitzroy Barrage. Credit to Tim Marsden, that's from his monitoring report. Basically, those calm conditions mean a lot of biomass can make their way upstream versus, I guess, looking at that Iceland one, designed for a specific species and a specific age range. Following up with something fishy part 1, there was talk about culvert design in the US. If you're doing culvert design in Australia, there's lots of great resources you can look to. So starting from the literature, Hubert up here in UQ, he's put a lot of effort into giving guidance and doing a lot of physical modeling around fish passage. So lots of good reading there. Depending on what state you're in, whether it's Queensland, that's that image on the right, Department of Fisheries have their own compliance requirements. So it's good practice to actually look to see what fisheries expects before you start putting these in. And depending on what your asset is, if it's a main road asset, or a CMA asset, they might have their own guidance as well. And if all else fails, you can always talk to an expert. Stepped pools, these 3 on the left, weirs, trapezoidal, and cone fishways, those are stepped pools. Basically how they operate is water plunges over the weir. You can see this image on the left. That's actually from this linear guideline. Now, that's an awesome guideline if you're patient enough to use Google Translate for French, or you can speak French yourself. There's lots of good examples, lots of good hydraulics. But looking between the two, you can see all that white water and high velocities. That's no good for fish in Australia because, again, fish can't throw themselves out of the water or swim against high turbulence or high velocities. This looks a lot nicer, that cone fishway. The hydraulics are pretty straightforward. If you have a flat weir, it's just that sharp crested weir equation. If you have a notch in the weir, you've got to include the notch equation. And as your water level, I guess this is supercritical flow, but as your water level begins to pick up on the downstream end and your weir starts to get submerged, it's important to consider submergence as well. Lots of good references here. Catapodus, he spent, I think, 20 plus years trying to quantify these different flow regimes properly. So he's got a lot of work out there. Villemont equation, if you want to read more about the submerged weir equation and getting that end value right, the end can trip you up. And I've got a paper coming out in the Hydraulic Water Symposium later in the year that tries to do the big literature review and quantify all of this. So lots of good reading here if anyone's interested. Vertical slot fishways, unlike that plunging regime for the other three, vertical slots, they're typically open baffle slots. So you get a meandering S-like shape instead. You tend to have more turbulent water, but much more calmer conditions, more uniformly distributed through the structure. You tend to get slow moving eddies depending on your baffle design. I'll just make a note, these two guidelines down in Vic, they're awesome. Suggest giving them a read for vertical slots. The hydraulics through vertical slot, that vena contractor, that's that velocity max that happens just downstream of the slot. That's just root 2g change in head between the slots. Your flow rate, that's just the coefficient of discharge by your velocity by area. But the CED is important to get right. If you have a steel plated baffle through your slot, you can have a much lower CD. But if you have something like, let's look at that epic monolith based down in Iceland, that might be your 0.85, 0.89 type of CD. So getting them right is important because that'll affect your flow volumes if there's water right concerns, and it could potentially affect your eddies and your turbulences and other things that'll spit out through your site. These two are the most common in Australia. That's your solid concrete baffle and your vertical slot baffle. The reason being, if you have something like this, all of your turbulence ends up getting focused here, and your smaller bodied fish can't actually find these lower moving parts of the pool. So evenly distributing, it's very important. Lots more references here. I think we'll link them at the end so people can dive in if they're interested. Mechanical structures, they're typically locks, lifts, and traps. We'll start with the lifts. This image on the right, that's from the Tallowa Dam down in New South Wales. I think it's the largest lift in Australia, but how they operate, an artificial attraction gets ejected typically around here, an auxiliary flow that gets typically diffused. So you have a calm attraction condition. Fish enter through the downstream and find themselves stuck in the lift at the bottom, and the lift gate shuts, the lift takes them over the dam. Sometimes you have a manual handling process that separates the invasive fish species from the native species. Locks are very different. They're typically semi-automated, and these come into play when you have a large dam wall and building something like a vertical slot isn't practical. Because when you're building a vertical slot, you want calm conditions, some low steps between each pool, and sometimes it's not practical unless the dam wall's 20 meters or even above 8 meters. Can't imagine how many steps you'll need to get upstream. So how locks work, again, artificial attractions created and hydraulic conditions are checked so you don't end up killing fish. The lock shut, fish work their way upstream, and then the lock opens later to allow more fish to enter. There's lots of trip ups that can kill fish, so it's very important you get the locks right. Undershot versus overshot. Undershot tends to kill fish just because of large differences in headwater between the two. So if you have a large headwater difference, you can scrape fish along the bed floor. You can cause, anything from frictional burn to fish death. So when you're designing, avoid an undershot as much as you can, unless you have very calm or very low headwater tailwater differences, and your biologists are also comfortable with the design. It's important that people that understand the fish also understand the hydraulics so they can make that judgment call. Overshots, you don't want a shallow overshot because you end up plunging fish into the ground, and again, frictional burns and possible death. So if you're designing downstream passage, I would always tend to go for overshot with a deep tailwater where you can. The design process for these larger structures can be very extensive. That involves lots of disciplines, but talking through briefly, I think Tim will go through in more detail, so we'll touch on this quite briefly. Starts off with the biology. You've got to know your biology to actually know what you're designing to. Let's say you're designing for fish migrating here in these uplands. You might actually be designing for adult eels that are migrating in very infrequent periods of the year and some adult fish. Whereas if you're designing here in this tidal coastal interface, you might be designing for everything from larvae, juvenile eels, juvenile fish down here. Frequently moving biomass of lots of small fish species and types and sizes is much more important than a select few types that are typically adults further in the uplands. So knowing where you're designing to and knowing your biology is very important. Knowing your hydrology is important because these small-bodied fish tend to migrate during base flow events, but larger-bodied fish migrate during actual events. So let's say you build a dam and you've lost all of this. How are you actually going to allow the fish to migrate again? What structure do you need? And what operational conditions do you need to keep the fish migrating? Moving from concept to IFC, it ends up being a very large process where you got to make sure your entrance attraction's right, because if the fish don't get to the fishway, they won't migrate. You've got to make sure that I guess the internals are optimized if you have gates or locks, that you're not causing harm to fish. And if you're doing the CFD stuff, there's a big optimization process you can take to maximize that biomass moving upstream. So I think that's it for me. On to you, Tim.
So yeah, today I'll just sort of give a bit of a background on fish passage and migration in Australia. So we've been working on fish passage for a very, very long time in Australia. It really wasn't until the early 1990s that we kicked off with some good studies that actually enabled us to determine fish passage for Australian species. Prior to that, we were importing technology that was less than successful at passing fish upstream. So why do fish undertake migrations? Well, in Australia, we're basically a country of drought and flooding rains. And so our fish species have adapted to these conditions. And so we have fish are restricted down to the last refuge holes during drought conditions. And then under the next flood conditions, they really take advantage of the ability to move to new areas that might not dry out next drought to maintain their populations. And it's really critical to maintain their populations, this movement between refuge holes up and down the river system. And so we tend to go through a bit of a boom and bust cycle with our fish communities, and that's really driven by their ability to migrate. If we cannot migrate from one section of the catchment that has dried out, fish cannot migrate to that area, we're no longer able to repopulate that section of the catchment. And so it's critically important that the refuge holes are protected. And then when the flows come back to the waterways, that the fish are able to move from the refuge holes that they've survived the drought in back into the other habitats that are within those river systems. Now, having said that, it seems that most movement would be associated with flood flows, which is generally pretty true, but we also have lots of fish communities that are maintaining links back to the ocean. So we have diadromous movement for spawning, and there's a lot of river systems in Australia that do flow all year round. And so basically, from north to south in Australia, we have fish communities moving on all flows at all times through the year. So it's really important. And there's a really wide range. Honestly, in our freshwater fish community and amongst our diadromous fish, pretty much all of those species undertake some movement at some point in their lives. Some of the very small species might only move 5 or 10 Ks between refuge holes and between their populations within those small streams. Whereas, we've got a lot of larger species that are undertaking very large migrations. And so things like bream and mullet might be migrating out of the estuary to go into freshwater to feed. Barramundi are living in the freshwater and migrating to the sea to breed. Murray cod move every year to go and find their favorite spawning log and spawn in that area 200-300 kilometers upstream from where they might normally live. And then there's a wide range of other species that are undertaking a great variety of migrations associated with flow conditions and their life histories. And when we're talking about these fish communities and what sizes we're looking at, we're talking about everything from these tiny little gudgeons on the right that are streaming through the Fitzroy Barrage fishway that Kyle showed earlier, So these are tiny fish that are around about 10 to 12 millimeters long, right the way up to juvenile, sub-adult sawfish, which are probably in the range of sort of 1.5 to 3 meters when they're migrating upstream. So, when it comes to providing fish passage for these fish, that can be quite a difficult aspect of being able to provide fish passage for giant sawfish and small juvenile gudgeons moving upstream. So we've got a lot of adults that are dispersing to go spawning, and we've got a lot of juveniles that are moving from their spawning habitat or their into rearing habitats where it's safe and they can get access to food so they can grow sufficiently. And so we need to know what species are in our waterway that we're working on and what sizes we're catering for to make sure that our fish passage is the right sort of fish passage. So what is considered to be a barrier to fish migration? Basically, any infrastructure that sits in a river and intersects with that watercourse is likely to be a barrier to some fish at some point in time. And so, whilst it's fairly obvious that the big weir there on the top left of the screen is a major barrier to fish migration, smaller barriers such as the small weir in the middle right there, the pipe culverts at the bottom, and the floodgates top right there, those also form barriers. They might not be a barrier 100% of the time, but they're probably going to be a barrier for a large portion of the time that fish are moving within these river systems, particularly on sort of medium to moderate flows. And why are these structures barriers? Well, generally they create a velocity step that make it very hard for fish to get upstream. As you can see, these poor little fishies are coming onto the apron of a culvert, and they're trying to get through that culvert and push upstream against that fairly high velocity that's coming out of that culvert. And unfortunately, we've done the maths, we've analysed the video. Every single one of those fish that attempted to move up and through that culvert all ended up at one and got swept downstream. And these fish are attempting this over and over and over again, and unfortunately, they don't get through. So, velocity is a real big barrier to movement. Vertical drops, water turbulence, swimming through very long, smooth surfaces is often really problematic. And also the reduced light levels that we may get in small pipes and things like that can also be problematic for fish. And so all of these things stop fish from migrating upstream. So what are the solutions? How do we fix fish passage? So, we always start with a sort of a stepped process. The first one we look at is, can we eliminate this barrier completely? Is it a used barrier? Are there other ways that we can do this that would provide passage without creating the barrier? So, for example, in this structure here, we've got a series of small pipes that are part of a causeway structure that obviously provide a velocity barrier, the long smooth surface that fish would struggle to swim against, and low light levels. And so that structure was deemed to be able to be replaced by a bridge. And so that bridge has allowed us for the natural channel to re-establish underneath the bridge and create conditions that are suitable for the fish to be able to move through. So no longer smooth, we've got a nice rough floor. It's very bright and open. It's not narrow and smooth, long and against smooth surfaces. So these fish are able to get through that structure quite easily. So elimination is the first option. If you can eliminate your barrier, happy days. Then we may go to sort of the next level, and that's incorporating best practice design into a structure. And this is particularly relevant in road infrastructure, where you're able to provide passage at some point during the flow regime. But with poor design, that might be 99% of the time no passage and 1% of the time some passage. Whereas with good best practice design, you might change that, flip that around so that you've actually got 99% passage all of the time and only brief periods when there's no passage. And that can be done by making sure that the culverts, for example, cover the full width of the channel, that there are baffles within the culverts that break up the flow and create low velocity zones that fish are able to use against the walls, making sure they've got a natural bed within that system. So by doing those things within these sorts of structures, we get that best practice design in place and create suitable fish passage conditions for fish. And then the final sort of leg of this trifecta is to go to a more technical solution. So where we can't engineer our way out by eliminating or putting best practice in place that makes sure that fish passage is okay, we can put more technical solutions in place. So we might have a technical fishway, such as that cone fishway up on the top left there. It may well be a natural type fishway down on the bottom left, the rock ramps and bypass channels. It could be baffle culverts and roughening of beds of existing structures within the culvert system. And then there's more technical fishways, such as the fish lifts and fish locks that Kyle was showing us before. And this is, you need to be aware of all of these options and how they may work with your structure, purely because the cost associated with these structures is so broad. The rock ramp fishway, might be able to be done for tens of thousands of dollars, whereas when you're up in a fish lift, fish lock, you're probably into the millions of dollars that is associated with those infrastructures. And so just sort of going back to Kyle's hydrology, the biology and the hydrology are what drives your design. And so when we're looking at our flow, we're looking at the drown out of the structure. How often is it drowned out? How long is it drowned out for? What then becomes a realistic upper operating range of the fishway? Probably in most scenarios, we can't make a fishway operate over the entire range of flows. So there's periods, once it's drowned out, fish are able to move past the structure. We don't need to make the fishway operate then. So we try and drag the fishway operation down to an acceptable upper range of operation. And then also we make sure that the fishway is able to operate all the way down to the lowest flows, because even though there's less fish moving on those flows, we still have significant movements occurring on those sorts of flows. And so this function of the hydrology really drives the design that we might be looking for at our fishway. And in some instances, where you have very large structures and very large range of flows that occur at these structures, it may actually be, in fact, cheaper to build two fishways rather than trying to squeeze that range of operation into one single fishway. And so, what you're trying to do is make sure that your fishway operates for the greatest period of times you can possibly get. And so you want ideally what you would have is that the lower range of the fishway is at commence to flow in the system. The upper range of the fishway is at right at drown out of the structure. And so then you've got fish passage available via the fish passage from low flow to drown out, and then via drown out of the structure above those flows. And so that combination of the biology and the hydraulics and the hydrology really drives the function of your fishway. And then that sort of, feeds into the cost and conservation values that you're trying to achieve with your fish passage. And so, that drives your capital cost and the operation and maintenance costs and your design life. And it ensures that, it doesn't ensure it, it leads to each of your structures having a very unique solution that's based on the site and the characteristics of the catchment and the fish communities that are associated with that. And to make sure that that happens, we need to make sure that we have a range of stakeholders engaged in our design process to make sure that we can take that biology, hydraulics, hydrology, the cost and the conservation outcomes that we're looking to achieve in our fishway, make sure all those stakeholders having input into our design to ensure that it gets the right fish passage solution for our site. And so to get from our concept design through to our final design, we need to make sure that we have this team of engineers and scientists, biologists, the owners of the structure, the operators of the structure, all working together to come up with a design that actually works for them. We need to consider the hydrology and biology and how that fits into the operation of the structure and how this moves forward. Often you'll have a site visit. It may be in person, or it could be a virtual one like this 3D animation on the right side there. And that gets everyone engaged, makes them understand what the structure is about. and how fish passage may be able to insert it into that structure. And that allows you to then, workshop through the designs, maybe do some multi-criteria analysis on the various designs that are available for that structure to come up with the best fish passage solution that, that shows you what the transparency of risk of the different designs is, which ones operate on which flows over which period and past which fish. Being transparent about that's really important, and that allows you to ensure that the expectations and outcomes that people have for the project are being met. So in general, the concept of final design starts with attracting fish to the fishway entrance, passing those fish safely through the fishway, and ensuring that there's both upstream and downstream migration pathways for those fish. I'll just put a little bit of a plug. I know Kyle and Steve will talk about some physical models and modeling. One of the things that we've been playing with a little bit is just 3D printing as a rapid design technique that allows you to rapidly change the design, throw it into a flume, and do a small physical model on the shot, on the spot sort of thing. And we've found that this is really useful to get us from something that's maybe not quite right to something that's working pretty well pretty quickly. Often when we go into the CFD and the physical designs, they're a bit more expensive and sometimes time consuming, and having a head start by doing some of this rapid prototyping with the 3D modeling can really help to get those processes moving that little bit quickly in time-sensitive projects. So in conclusion, I think fish passage should be incorporated into every weir, dam, road culvert, and it's just an integral part of the design of those projects. We need to make sure that we've got the attraction of the fish to the fishway or fish passage elements, and that the passage through those elements is successful. And that requires teamwork from engineers and biologists, working from the business case. And this is a really important thing that I'll really highlight. Making sure that you've got your engineers and biologists working on fish passage at the business case stage of your project ensures that suitable fish passage is included early on and that there's no nasty surprises later on. We have a lot of projects that don't consider fish passage particularly well in the business case and might put a nominal value on the fish passage, and then when they get to their approvals process, find out that they're up for much more significant fish passage than they expected, and of course that gets everyone in all head up because their budgets have been blown out. If that budgeting is included in the business case early on, you don't have that many issues associated with that. So so I think that fish passage should be included. Everyone should look after it, and I think the modelling that Kyle and Steve and whatnot are doing is really helping us to understand how these fish are getting upstream. So I'll leave it there.
Okay,
I'll make a start.
Let's get cranking. Thanks.
Thanks, Greg. And thanks, Tim, and thanks to Kyle. Look, I think Tim had some very good points about the cooperative approach to fishway designs, and I think I'll touch base on that. I'm going to be looking at over the next 10 minutes or so. I'm going to look at a specific aspect of fish passage design, which is getting the fish in the entrance, getting them to find the entrance and go in, and also to get them when they get at the top end to actually when they come out, so they don't get returned back downstream, so they can safely go on their journey upstream. A little bit of context to start with, and here we are in Australia. Tim, Kyle, and I, and what we're looking at here on the map there is the Murray-Darling Basin. It's that's the size of it at the top there, 1.05900 square kilometres, about 4 times the size of Great Britain. It's a very big river system, meandering river, quite flat. It's very slow moving, meandering, but we do have a limited number of native fish species. And generally they have poor swimming abilities because the river's so flat. So I suppose from America wise, you're probably picturing something more like the Mississippi than you are, say, for Pacific salmon or anything like that. So we have our fishway designs have to have effective attraction to the downstream entrances and safe exit from the upstream exit. So this is what we're concentrating on here, and This little blue line basically shows the route I actually drove about a week ago to get from Adelaide. So Brisbane was 2,000 kilometres, so it's quite a long way. And here's a map of the Darling, the picture of the Darling River. Just last week with some overbank flow happening. Some of our fish, we have small, medium and large size fish, but anywhere in the river system, typically we're getting only about 12 to 15 species of fish. So you can see at the top there, we have a small fish, about 30 millimeters. And then we have a bony herring at the right there, which is medium-sized fish, going up to larger fish species like silver perch, golden perch being one of our more iconic species, and our very iconic species being Murray cod. This one's a small fish, small cod, but they actually grow up to about a metre plus. So fishway attraction. So what are we trying to do? We're trying to get the fish to go in the entrance of a fishway. And there's two rules, two key rules. One is that the fishway entrance must be at the limit of upstream fish migration. So that's either a physical barrier or a zone of turbulence that the fish can't pass. The fish will go left and right across that zone, and then needs to find the entrance. If the entrance is too far downstream, the fish will go past the entrance and won't find it and won't go in. Conversely, if the fishway entrance is too far upstream and it's shielded by turbulence, the fish can't find the entrance again. Also, fish must follow positive attraction flows to locate the entrance. So this basically shows a site here down in South Australia. We've actually got submerged nib wall under this structure. We can two overshot gates with some high turbulence behind the nib wall. And here's my little Murray cod coming up the stream. They're actually hiding below the bottom of the nib wall. They won't go into that zone of turbulence because you can't stay in there very long because it's too turbulent. And they pick up the flow out of the vertical slot fishway entrance, and then they go. So that's what we're trying to achieve. And there the fish were shooting below the nib wall there. So a worked example is the pike and tannica regulators and fishways, which are at Renmark here. This scheme has two similar structures with gates, bridge and vertical slot fishways. And the schemes to actually provide managed inundation watering of the Pike floodplain down by Renmark at Lock 5. So you can see here that we have the regulators, and you can see the fishways at the abutments there, vertical slot fishways, and they're low turbulence fishways. We're trying to get small fish about 30 millimeters through there. So how do we do this design? We actually used the University of South Australia Australian Flow Management Group to construct a 1 in 15 scale physical model of our concept design, and that had lay flat overshot regulator gates made out of steel plate. And the features were the entrance and the abutment. You can see the vertical slot there. We also had 6 lay flat gates, some piers, a flow straightening wall because we're trying to protect the flow vectors at the entrance. We had a primary flow from a primary pump coming through, and we had a secondary flow simulating the flow out of the fishway. And so what we did with our physical model, we just modeled a whole range of flows and water levels to optimize our entrance conditions. The key attendees at the modelling are the designer, the fish ecologist, the owner and operator, and other key stakeholders and improvers. This is very important and touches on what Tim was saying, is that it's important that the ecologist understands what us, the engineers, are actually designing. It's that relationship is very important, and using any model, let's say a physical model or a CFD model or any kind of design, is really important that the fish, the modeling represents what the fish are actually going to do and go in. Because if not, you've got $many million fishway that's going to be built. If the fish can't go in it, then it's a failure, and we don't want that. So the key benefits of the physical model here, we actually had a hands-on approach here, and you can actually see we got engineers, and there's the client standing at the left. We had a rapid assessment of options once it's built. So it has a lead. This model had about a lead time about 6 minutes, 6 weeks, sorry, and about 2 days testing. And of course, the fish ecologists had the inputs. And there we had our primary flow, our secondary flow, a surge tank to take out the surge upstream, and a regulator gates and a flap gates. So our flows, basically what we were trying to do is get the fish to go towards the entrance there. And so we actually operated the gates near the entrance there, and we actually adjusted the model to actually get the traction flow there. So the fish moved up. We actually incorporated a nib wall, and we had a zone of turbulence which the fish would not go in. And here's our fish swimming upstream, and in they go. So this was the kind of things that we were putting into our model to actually get our fish to find the entrance and go in. And of course, on the upstream side, we also looked at, are they going to come out safely and not get returned back downstream? Here's a scenario for a higher drop, but showing a similar kind of thing there with turbulence, flows, and high velocities over the top of this nib wall there, and the fish would basically come up there and actually come across and go into the entrance slot. And again, we also did flood flows as well. And you can see that we actually have something that's actually very flexible. So we were flexible, be able to cut and shut the model to get the entrance slot in the right location, but also to change all the gates and flows and settings, so we were comfortable that the fish are actually going to find the fishway entrance for all flows. And this is basically how we set it for that. And again, here comes our fish. This is our Murray cod. And whilst we didn't put fish in the model, because that was kind of well, it kind of has ethics problems as well. You need to actually put the fish in the model. So we actually just use other instruments, which I'll show in a second. So hopefully this will play. If not, it might be a bit too clunky. No, it's a little bit clunky, so it's not going to play. Oh no, there it goes. So basically, this is just showing the flow running through the model there with our gates fully open at a flood. And what we're doing is we're just assessing the fishway entrance for this condition here. Our tools of the trade, and we basically, sorry about the jumpy video here. I think perhaps we were a little bit excited, but what we're doing is we actually have Dr. Ivor Stewart standing in the foreground, a fish ecologist. He's actually holding a velocity meter to assess water velocities and attraction flows to the fishway entrance. And that's me. We're basically putting some dye into the model to actually to show what the strengths of the flows are and what the velocities vectors. So we've got integrity of flow below the fishway entrance. And this one's a bit more stable. We're basically just showing the velocity meter, and we're basically just assessing the direction of the flow. And you can see we've actually, with the orientation of the wing walls of the structure and the orientation of the fishway pointing straight downstream, we're actually getting some very good currents straight downstream of the entrance of the fishway. And we were actually comfortable through the modelling that we were able to demonstrate that the fish would be able to find the fishway entrance in this model. So now to our 1:1 scale model after it was built. And what we can see here, this is the Tanaka structure showing the fishway entrance here at the left, putting about 30 megalitres a day flows straight down the wall here. We've got our 3 overshot gates passing our flows up to 546 megs. We actually have some nibbles below there, and we are able to think, okay, well, we actually achieved the flow vectors below the fishway entrance that we wanted, which was really good. So we think, okay, well, that looks like it's as representative of the physical model. We were quite happy in the field. So just another one there, just basically showing, you can actually just see there's a bit of surface slop there, but the fish will be down deep, and we're actually getting some good attraction flows coming down this wall here. So the fish will be moving along this wall and straight into that entrance slot at the limit of upstream fish migration. So did it work? Yes, it did. It was. So this is on the same day. I just took that last video, and we had Sadi, who is our local research and development institute here in South Australia, doing fish sampling at the fishway entrance and exit of both the Pike and Tanaka structures. And you see here that we We had a very good range of the target fish species and sizes greater than 30 millimeters of body length. So we had some bony herring, golden perch, and even Murray cod, which we weren't expecting. And the lady on the bottom right hand there, she's actually holding a medium-sized golden perch, and we had a lot of golden perch through. So, as I say down the bottom there, whoop whoop. That's it was a good result, and so the process of going through the modeling actually, and then taking into the design, and then going through and then doing the sampling, we showed that we had a really good result. So just wrapping up, I've said here CFD or physical model, and I suppose it's, why not both? I think both can be complementary to each other, and sometimes it might not be just one or the other. Both are horses for courses. They're useful tools at our disposal for use in fishway designs, and there's pros and cons of each. Like a physical model does take several weeks to build, but you can actually test it and get through all the regimes and get the ecologists in there. But again, they are complementary. CFD and physical modeling can be complementary. But the key one here is that fishways are very expensive to build, typically, and the cost of modeling to get the design right represents just a small cost overall. So, if you don't do engineering with the ecology, also with the operation operation and maintenance, then you get problems. But anyway, there were some acknowledgements there, but thanks, team.
Thanks, Steve. What's everyone's thoughts about doing the QA now? I know people would be very interested in the QA, and I can always drone on about more advanced hydraulics afterwards.
Yeah, we could always slot that in. Yeah, let's do that while we've got everybody on, at least to get everybody to, because we do want to make this interactive as possible.
Yep.
So yeah, Tim and Steve, if you want to just come on and maybe just highlight a couple of the questions that you've answered. We like to go with the ones that have been upvoted the most, and maybe we'll just start with one of those, and then Kyle, I'll let you just take over. The one,
Yep.
People asked about, a lot of people wanted to know about the velocities, and of course the answer is, well, that depends. But would you mind just giving a range, like in different areas, in meters per second, and maybe we'll have to do the translation for the Americans on here.
Really comes down to the species and size, Cray?
But what's it? Give a typical range from in different areas of the world. Can any fish go 6 meters a second, 3 meters a second, 2, 1, half a meter? What are those ranges?
Yeah, generally we're below that sort of 1.5 meter per second range. Once we get above that, so the velocity is all dependent on the ability of the fish. It's like all humans. We have different fitness levels. Well, fish have the same sort of thing. Some of us are great at sprinting 100 meters, and some of us can do that 20 or 30 times, and then others can't. And so, generally what we find is that if we below 1.5 meters per second over short durations, so very short distances, many fish can pass that. But then, as we head down to some of the maybe coastal environments where we've got very small fish, our velocities drop off significantly. So, in coastal systems in Queensland, for example, we might need velocities down around the 0.2, 0.3 meters per second mark to be able to pass these tiny, tiny, tiny little fish that are coming back out of those estuarine conditions and moving upstream. And then, where you've got more adult fish that are moving, you can have those higher velocities. So that's one of the key challenges within our fishways is getting the velocities to the right level and the right distance. If you're in a culvert, it's very long and skinny, so the velocities have to be very low. If you're in a baffled fishway, for example, the distance the fish have got to swim against high velocities might be only centimeters, so you can go a little bit higher. So it does depend, unfortunately. Sorry, Craig.
Yeah, the rule of thumb was always 1 foot per second, so 0.3 meters a second for everything we did in the Pacific Northwest. But just wanted to put those bounds on things. Kyle, I'll let you just lead the rest of this. Hand off to Tim and Steve as you see fit. Then.
Yeah, I think adding on to what Tim was saying as well, you got to really design for burst speeds between slots and fatigue over time. So knowing your biology again, very important.
That's correct, guys. And the other, and I think Tim, you touched on one of the key the three key aspects, which is velocity, but the other key things we have for Australian fish is poor turbulence, and the turbulence has to be pretty low, and also we have to have sufficient water depth as well. And typically the rule of thumb that I've been working with is about 1 to 1.2 meters water depth in the fishway for the passage of the largest size fishes. Down to 30 watts a cubic meter, we'll get about 30 millimeter fish through, and slot velocities for a 30 mil fish is around about 1 to 1.2 meters a second in the slot. So yeah, our fish are pretty poor swimmers, and we
That ability to
things
rest
very
is
quiescent.
Yeah, that ability to rest, Steve, is really important as well. What we're finding in these with the really tiny fish in the coastal systems is they're just running out of energy up the normal fishways. And so we're having to provide practically dead water zones where there's just no velocity at all. So these fish have a chance to recover from those sprints. And we're also considering things like looking at feeding stations within these fishways to allow these very, very tiny fish to re-energize, because they basically just run out of energy. And when they do that, they're really vulnerable to predation. And the many fish, like the catfish, local catfish species, they get into the pool that's got the most number of tired fish, and they just clean up and take out whole year classes of fish. So.
Question for you, Steve. There's one here. Why isn't revegetation more incorporated into the design? So there's Murray designs you've shown.
Revegetation?
Yep.
Well, not so much in the fishways themselves, but that is a whole different field. Is that within the river systems itself, a lot of the timber has been taken out, and rocky reefs and things like that through colonization and use of the river systems. So there is a big push to reintroduce flowing water habitat in less stagnant or stable pools and more flowing habitat, and actually put in back in the timber snags where the large fish lived. Unfortunately, a lot of all the in-stream snagging was removed without realizing what the impacts were until it was kind of too late. And so there's a big push on now to get rid of the more canaled look and get more of a natural look. But in the fishways themselves, we're just trying to get the fish in and out. But there are different fishway types other than vertical slot fishways as well, and we can actually have things like rocky ramps and things like diversion channels and things like that, which can be vegetated. But in this case that I presented, we were just looking at a vertical slot fishway to get past a gated regulator, which had fairly complex hydraulics.
I guess re-veg is a long-term solution as well. So short-term, you need to get fish into the entrance and through the structure. So rocks work in the short-term, re-veg in the long-term.
That's right, and that scheme I was talking about with those two structures, which is the Pike floodplain. The whole basis of that whole project is that it's to actually introduce managed inundation watering of a floodplain over 1,000 hectares, which is bringing back some very key habitat for not just for fish, but for all birds and frogs and tree health. So
There's one question for you here, Tim, from Nick Green. It's on fish lifts and I think the Telewrap. So if you want to give that a read, and I'll just answer another question here.
No, I've already read that one. Look, it's difficult with the exclusion of fish, non-native fish from fishways. In all reality, non-native fish dominate river systems that are in poor condition and have got poor water quality. Recently done some sampling up in some very pristine condition streams up in North Queensland that have got riparian zones and in-stream habitat and water flow and good water quality. And guess what? The tilapia are there, but so is everything else. And so my answer to that is that don't exclude them, make the habitat upstream much better so that all the native fish can compete against them. And I know it's a bit hard, and it can often be a bit traumatic for people to see these non-native fish going through. Certainly in some areas where there are not native fish, those non-native fish are not above those structures, you may actually consider not including fish passage in those structures because, just to stop the spread of those fish to those areas. So.
Steve, another one for you. How do fish actually find the entrance?
Yeah, attraction flow. So yeah, positive attraction flow. And yeah, you got to basically, so you have it so that the fish move up, and this that entrance has got to be right at the limit that they can swim to. So if the gates are too turbulent, they'll move left and right, and they'll pick up that flow coming out of the entrance, and they're looking to move upstream as far as they possibly can. So it's a very important rule, is to have that entrance at the limit of upstream fish migration. They'll pick up the velocity, and you need it enough so that the fish are attracted and not so. And so that's the way upstream. So usually we're aiming for about a meter a second in the slot itself, and that draws them into the fishway. And once they're in, we know a lot about vertical slot fishway hydraulics. Once they're in, away they go. They'll swim through. Getting them in is the catch.
We keep we consider the attraction flows that Steve just outlined there as the equivalent to a flashing neon sign saying "Enter here."
Yep. Yep.
Not here where it's ripping through, right?
Yeah, that's exactly right.
Yeah, and of course, I think in Australia, probably the same as the rest of the world, like there's lots of examples over time of things that have worked well, and there's lots of lessons learned with things that haven't worked well. I think one of the key ones is, I think originally a lot of our fishway designs back in the day, 50, 60 years ago, we were looking at, we had like the salmon, trout type fishways, and these steep fishways were built. Yeah, and then they're sitting on these structures still, and they've never passed a fish, So yeah.
There's one more
Lessons
here.
learned.
There's one more here from Mark Groves. He's asking about, is there an industry agreement on the appropriate CFD turbulence solver? So stick around after the Q&A and I'll try to tackle that question. Yeah. Lots of dispute, no agreement, but yeah, the industry's getting there.
No, that's awesome. Yeah, so maybe just another minute or two, just a couple questions here, and then we'll get into Kyle's bits. In the meantime, though, I see a lot of comments, about local guidelines here or there in different areas. What I've set up for the first Fish Passage webinar was a website, surfacewater.biz/fish, where I've got resources listed. I'll continue to put anything you put in the chat line. If anybody knows their local guidelines, we haven't been able to comment on some of those. We've got a global audience, even though this is Australian focused. If you've got some resources that you'd like to share with this group, a couple of hundred of water professionals interested in Fish Passage, we want to help anywhere we can. Send those resources across. We'll post them to that website. It'll be in the YouTube description for anybody who comes across either of these webinars going forward. Let us know, and we'll keep that website going so that we can pass along all the resources that you might be interested in. So Kyle, just a couple more questions, and then let's get into your technical
Got a good
bits.
one here from Rod. He's saying, great presentation, guys. Without real fish to test the physical model, how do you determine if they'll find the entrance? So I was reading an interesting study recently out of China, and they were trying to extract turbulence from CFD models and validate it with a physical model, and they had the fish going through, but those were starved silver carp. So even if you actually put the fish in the physical model, if they're hungry, they'll behave differently to when they're out on site. So really what you're doing is you're relying on people like Steve or Tim to look at that entrance attraction, look at that hydraulics and go, yeah, for the last 20 years, I've seen sites like this, and that's worked for these species of this size. Or that doesn't work because undershot killed the fish, don't do it type of thing. So relying on experience.
Can I just add to that? Yeah, you're exactly right. There's a lot of knowledge in Australia here about what works and what doesn't. And every time we develop a design, we're always learning something for next time. But when we're actually designing new regulators and fishways, as a fully new structure, that's a little bit more simple. But when a lot of our structures are weirs of being retrofitted with fishways, and every single design is different, and it makes it very, very difficult to actually, you can't get a one size fits all fishway solution. I mean, the process is the same for dealing with it, but the designs are typically different.
Yes. All you need to be able to do is scale those fish. Let's get some scale model fish to swim up there so they know the food numbers and everything.
Yeah, I think Steve made a really important point there. I think I sort of talk about my 30-year career in Fish Passage, and I've built hundreds of fishways, and every single one of them is an experimental fishway, and I have not yet built the perfect one. You know, I build it, I design it, we build it, we monitor it, we learn from what we did, we make the next one a bit better, and then we find out, you know, what was right or wrong with that one to make the next one better, to make the next one better. And we've still got many years ahead of us before we get to the ultimate perfect fishway. I don't think, you know, that's, you know, we'll see
Chasing
out
a
my lifetime,
dream.
that's for sure.
Yeah.
Yeah.
Kyle might have
Nirvana.
half a chance.
You might, the fish might evolve at that point, and then you're back to square one.
Yes.
Yeah, there we
100%.
go. Joel, if you can share those last couple of slides, and then we'll have Kyle take over. But just so for those who need to run on the hour, I know some people do this on their lunch break. Just keep in mind, everybody will get this recording link, and you'll get a certificate of attendance as well. This does count toward continuing professional development, so stay tuned for future webinars as well, and do help us steer next year's. We're in the process of planning, 20 more webinars for next year, for 2023. What topics do you want to see? So let's, go ahead and participate in that, because we do this for you. Got a couple of courses coming up just in a few weeks' time on rating curves. So we would love to have you join us for that. We're going to get hands-on, talk about gauging and turning measurements into discharges and what the potential pitfalls might be. A lot of other topics coming up, especially some relevance next week with the mega drought going on all around the world. You got all sorts of, rivers going dry and lakes going dry. If you want to learn more about the water resources impacts of that, join us next week. So with that, thanks to everybody for attending. If you can stick around with us, Kyle's got some cool things to show. Otherwise, tune back in on the recording to have a look at that. So Kyle, if you want to start sharing your screen, and we'll close it up after that.
Awesome. Just double checking we can see my screen.
Yep, all coming in just perfect.
Awesome. All right, advanced hydraulics to try chase that perfect design Tim was talking about before. Probably won't get there, but at least in the CFD and physical model space, we're trying our best. I'll cover this stuff quite quickly so we can get to the CFD, but that's Tim's flume on the right, and he covered it in quite a bit of detail on that link at the bottom, that AWS webinar. So if you want to learn more about Tim's flume, check it out. But the really good cost-effective way, well, the really good cost benefit of the flume is, let's say that one's out in Tim's backyard. He can 3D print a structure, start running water through it, and start looking to see where those eddies and those velocities are going. So rather than building a physical model, which might take weeks, or doing an optioneering approach in CFD, which could take weeks or months, you can kind of knock out those undesirable options early on. And it looks cool as well. So the physical model, that's the next step up from the flume. Generally physical models, as Steve was showing before, they're scaled based off well-known hydraulic principles, whether that's Froude numbers, Bernoulli's equation. Physical modeling goes back probably 100 years at this point. It's well studied, well understood, and using those pressure gauges, pressure sensors, velocity readers, you can extract pretty exact results and then scale those results based on those hydraulic principles to get, I guess you'd call them highly probable outputs for your structure. Physical modeling can be very expensive. There's real estate costs to dedicate a part of a lab. Materials costs are going up, whether it's concrete, steel, even the finer gauges that are hard to come by now. And you need to have a good lab technician that understands the entire process. I guess the pitfall of physical modeling as well, it struggles to replicate extreme conditions. So let's say cavitation, or if you have a big scale difference, like a 1 to 500, your uncertainty bands go up as your physical model approaches the actual site size. But physical modeling's been done forever. It's used on large dams to this day. They obviously get good results. Dams aren't typically failing. So CFD, it can be quick to set up. Let's see if that animation plays. Yep. CFD can be quick to set up if you scale back your solver and scale back a lot of your assumptions. But as you scale those things back, you're creating uncertainty. So you can do an optioneering approach where you're doing, let's say, 1 optioneering run a day. That's not even close to the Tim flume, where you could optioneer on the fly and do 1,000 tests in a single day. But at least CFD is becoming a little bit more practical. It can often carry the design through to IFC, but if you're doing an important structure, that large dam, there's a lot of uncertainty, then best practice is to use a CFD model in conjunction with a physical model. When you're doing things like fishway internals or smaller fish or fish passages in general, very rarely would you actually need the physical model to validate the CFD model. CFD, you can model non-Newtonian flows, sediment transport, all sorts of things, and extract depth varying results whenever you're ready to really cut apart all the finer details. There was a question about, have best practices been established? And unfortunately, no. In the consulting space, a lot of CFD engineers have tended to keep their findings and keep the methodologies to themselves, which is pretty unfortunate. But there are government bodies like Sunwater, TMR, at least up here in Queensland, that are starting to do the modeling themselves and starting to establish their own best practices. So I guess hoping down the track, they'll actually begin to drive how we should be doing the modeling and what the right approaches are and outcomes are. When you're doing the modeling, you can change a small input and suddenly everything changes with your outputs. So it's important to have a good literature review and validation when you're doing your modeling. And as I was talking about before, you can create project timeline drag if you're stuck in this optioneering stage. CFD is nice because it's basically high school physics, but gets more and more complicated as you do the numerics. You're solving conservation of mass, momentum, and energy. Energy we don't really consider typically in the fish passage space. That'd be more like, I don't know, maybe welding, or when you need to include heat in the system, then you need to start consider conservation of energy. The conservation of mass is fairly straightforward. Mass you can't create between cells or between solvers. Mass can't appear out of nothing. Conservation of momentum, it's just F equals ma effectively, but a lot more complicated, where at least if you're looking on the right, you're trying to solve external forces and pressure gradients, fluid viscosities and viscous effects, your acceleration, change in velocity over time, and in that acceleration is the change in direction of fluid as a gradient as well. CFD, you're stacking cells in the X, Y, and Z column, if you look at that image on the left. So you're actually you're getting a depth varied outcome, which is important if you're trying to get, if you're trying to work out how those smaller bodied fish are swimming towards your bed. I'll touch on 3 things briefly that are coming out in that paper later on in the year. Reach out to me if you want a copy, but 3 things I'm starting to find are really important. You should always check with your CFD modeling is your mesh resolution, your turbulence model, and your wall roughness. I guess we'll start at the turbulence model there on the right. Let me just grab my pen quickly. There on the right, this here, that's a large eddy simulation, LES solver. And how LES works is it filters out the very fine eddies. So you end up getting these smaller eddies that are retained within the solver. And filtering out the finer eddies, you can save on computational time and expense. So LES can be practical depending on your cell size and the complexity of your model. The one on the left, that's an RNG RANS K epsilon solver. Effectively, it's a Reynolds average Navier-Stokes solver where, depending on the package you use, it might just average out that Reynolds number for the entire model, or it might create domains within the model and have a Reynolds average number through there. And within that vertical slot simulation, you can see that that same path is still captured between both, but we've lost some of those finer eddies if we use a LES solver. But LES is very computationally expensive, so that might not be practical for what outcomes you're trying to get out. Wall roughnesses, it's important to know exactly how your roughness is applied in your model. It's very different to Manning's. I'll touch on it a little bit more. And cell size is important. You need to adequately capture your mesh geometry properly if you have a chance in solving turbulence, velocity gradients, and all these other things properly. Unstructured meshes, these have fallen out of favor because let's look at this corner right here. That's an incredibly fine cell size, and if you have to solve the Navier-Stokes properly, then it just takes forever and creates timeline drag. Having a structured mesh solves a lot faster, and the results can be fairly interchangeable. There are some papers that people are interested where for this civil water CFD space we're in, structured tends to perform better than unstructured. The appropriate mesh is one that captures the geometry adequately, maintains reasonable run times, and provides defendable results. That defendable results portion is very important because you can plug anything you want in a CFD model, get an output quickly and go, that's what it is. But then you'll find out later, you've basically made stuff up for a project. So it's important to do that literature review. There's lots of rules of thumb here to get your geometry right. And if you look here on the right, that's a steel plated baffle with a coarse cell size. And even though I've captured the baffle shape right, the results change very quickly. And that's because you need a minimum number of cells in the X and Y and a minimum number of cells in your Z to adequately capture that flow gradient properly. I'm not going to touch on it here, that universal law of Wall and Y plus, but those are also important to get that velocity gradient and that pressure gradient right out of the model. And cell size is also solver dependent. So if you're using a different turbulence model, your cell size assumptions can change. Turbulence and roughness. So these are the big three on the left. K-epsilon, that's that average solver. RNG, it's modified K-epsilon that handles low Reynolds number and those near wall functions. That's that Y plus a little bit better. So I really like RNG unless I'm doing a large eddy simulation. Wall roughnesses start to get very tricky. Effectively, it's a roughness applied to that bottom cell, and your roughness tends to become asymptotic as it approaches the cell centroid. And asymptotic basically means it starts deviating from the value it should be. So getting enough cells in your velocity in your z-axis is important, but also understanding your minimum cell size to solve that Y plus properly, so you get that gradient model correctly, and understanding how your roughness might interact with your cell size, and then how your turbulence model might interact with those cell sizes as well becomes very important. They're not interchangeable, and it's important to understand the differences between each. There are ways around that roughness limitation. You can actually physically model the roughnesses, or you can apply, I've read a few papers where they've put a defined shear force on the bed, and that shear force has artificially created that correct velocity profile. It's not great, but I guess a lot of engineering judgment needs to go into these models. That's an extract from the paper. Basically, using coarse cell sizes, you can see this here is a fine cell size with that average solver and that filtered solver, LES. And looking between these vertical slots, you actually need a very high level of detail and very fine cells to actually get that flow properly. If your cell size is too coarse, you can end up looking like this. And then, Tim or Steve will see something very different once they build it out on site and go, what are you doing? Let's look at some animations. There's a nice little video I suggest everybody check out online who's interested. But basically, it's an animation of how fish approach a weir wall, and they find that attraction flow. And when they find that attraction flow, they stay away from the high turbulence, high velocity going over the weir. They enter the fishway and keep migrating upstream. So the Flow 3D team, they tried to model that to kind of see how it operates with a partially drowned condition. And yeah, you can kind of see it in action. Water coming over, lots of churning, lots of eddying that then enters the fishway. We tried to do a very coarse optioneering approach to see how it will all turn out. So this is a base case. There's water plunging over the weir. And you can see there's an eddy in that corner as water plunges over the weir. So let's say we put our fish passage in. And if the fish passage is perpendicular to the structure, you start to get a fairly wild eddy that's occurring at the entrance. So fish aren't going to be able to swim against that eddy. Let's say we open it up a bit more. That eddy just gets bigger. So it's no good. Fish aren't going to be able to break through that eddy to swim upstream. And let's say if we make the entrance parallel, starting to look a little bit better, but there's still that 0.3 to 0.6 meters per second eddy, so still haven't got there. You can start to see how these projects, if you just go through CFD at the optioneering phase, can create a lot of drag. So now we've added a shallow deflector and we've upped the operation conditions, and the eddies broke, which is nice, but now we've actually created a new problem. All of these greens and signs, those are high velocity zones. So the eddy's gone, surely the fish will be happy. Nope, the velocity's too high now. Other nice animations, modeling channel flow to work out entrance attraction. I think this is a buried shallow dike, and you can see on the left, it's created a lower velocity zone. So maybe where that plunge is happening, something like a vertical slot or a small structure might be able to improve the fish migration. Modeling internals. Here's a nice video from Steve, and this is vertical slot fishway in action. You can see on the right of the wall, the water level is lifting up a little bit. I'll grab the laser pen. It's a little bit of lift up here, and there's that S-shape meandering through. So with the CFD model, it's quite nice because, at least in this case, I think we've got a model agreement of plus or minus 1 to 2 millimeters to the site, which is quite nice. With the CFD model, we can model that either before it's built or, I guess, validate the solver to the site data. And from there, you can then extract flows below the baffle inverts to see all those karma conditions, to work out if juvenile fish can pass upstream, work out where the high turbulence zones are. And I guess that might tie into that optioneering process where maybe you'll change the baffle type, shift the baffles, move the baffles, increase the pool area, pool volume. Once you get that validation, it becomes really nice to, I guess, as Tim and Steve would say, chase that perfect structure. We're almost there, just locks and gates left, but opening a lock in a shallow condition, I mentioned how you can kill fish or cause frictional burns. With CFD, you can extract those velocities and go, all right, that's like between 20 to 30 meters per second. That's no good. Maybe you need artificial, additional auxiliary flows pumped in to create a calmer hydraulic condition as the gates open. Maybe that might be acceptable for a brief moment of time, but that really depends on the asset owners and the species you're designing to. Opening a gate into a plunge pool, whether it's fish coming over the gate or it's fish that are already sitting in the plunge pool, you can work out quickly what those velocities and turbulence zones are, if they're impacting the fish or not. Again, we can do all of this as a hydraulic engineer, but it comes down to interpretation by the biologists or the fisheries advisors. And I think that's it for me.
All right. Wow, Kyle, thanks for that. Love
Sorry
seeing those animations. No. What that did, typically what happens is everybody waits and then asks questions toward the end of the presentation. Then we cut it off and nobody gets their questions answered and we have to do it offline. But this presentation gave Tim a chance. Rockstar there, Tim, thanks for doing that, to answer pretty much all of the questions, like 30, 40 open questions. So thanks for that. We'll try and post those, since those watching the YouTube recording won't see the questions, we'll try and post those to a PDF file, which we'll have later on. So no, thanks for that. Yeah, if there's any, we'll just do some parting shots from everyone. Kyle, I guess probably your biggest challenge, actually, I want to see you pronounce that that site in Iceland that you showed earlier on the site.
I actually spent a few days using Google to translate it, but nah. I already can't pronounce fish species. So.
All right, no worries. So what we'll do is let's go back in back through in the order. We'll have Steve, then Tim, then Kyle. Just give us your closing thoughts, and then we'll sign off for the day. So Steve, if you're still on, just if you can turn your camera on, just let us know.
Yes, I am. I'm just struggling to get the camera on. But
no worries. Okay, we'll hear your voice then. That's all right.
Yeah. Look, thanks for inviting me along to present with the team here. Look, it's been great, and within our industry, it's always good for us to actually share what we know. We there's a lot of knowledge held by relatively few people in the industry here, and we're always keen to actually make the industry bigger, because we have several hundred weirs which need fish passage built on them over the next few years. So thanks everybody for the invite. Cheers.
Okay. Over to you, Tim. Closing thoughts.
Yeah, look, I think it's been great that we've sort of presented some of the more Australian stuff for fish passage things. So, really, you've got to consider your local species, and you've got to have some knowledge. So seek out your experts of what those fish species are and what their swimming abilities are, and that will stand you in good stead with any fish passage project.
Cool. Kyle, bring it home.
I think the big thing is don't operate on hope. I know you can be tempted to, we can save the client, let's say 100,000 and dumped rock or grouted rock. So maybe it'll work. It's very important to go to those experienced few, or read your guidelines, read literature, and know exactly what you're designing to. Because the last thing you want is to end up in enviro law, end up on the news, or just, be named and shamed for killing fish. And
good.
With mechanical structures, it's important to do them right.
Yeah, and use the tools that are available. They're continually improving. And that's a plug for the Australian Water School courses. Sign on up for some of these. We will be doing 3D modeling next year. So if you want to try this yourself, let's join us for some of that. And anything that you'd like to see more of, please let us know in your feedback. So with that, thanks to your presenters. They've come on as volunteers for you, for the industry, globally and here in Australia. So thanks so much for coming on and volunteering your time for that. We really sincerely appreciate it. It's a small world. Let's stay in touch, and let's expand this science so that everybody considers it when they're doing hydraulic designs. And let's make sure that some of these things are incorporated so that we can make the planet a better place. So with that, thanks for joining us today on the Australian Water Schools webinar series. We'll see you next time around.
Thanks, guys.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.